Ever stare at your phone or computer waiting for it to load and feel like its brain is just thinking way too slowly?
Happens all the time, right?
Yeah. Or maybe you've heard all the buzz about AI and wondered about mind-boggling energy it demands. You got to ask yourself, is there a better way?
The huge question.
What if our digital devices could literally think right inside their memory? Instead of, constantly shuffling data back and forth like a librarian, running laps for every single book request.
That's the dream. Avoiding that shuffle.
Okay, let's unpack this. Today, we're diving deep into a truly groundbreaking technology. It's called resistive switching random access memory, or RRAM for short.
Yep.
And it's not just some fancy new chip. It seems poised to fundamentally change how we store and process information. Potentially transforming everything from the smartphone in your pocket to, like, the most advanced AI data centers on the planet.
It really does have that kind of potential.
So this deep dive is based on an incredibly comprehensive review. It's titled Resistive Switching Random Access Memory, RRAM, Applications and Requirements for Memory and Computing, and it was published in the journal Chemical Reviews.
A really thorough piece of work.
Absolutely. And our guides today are the brilliant minds behind it. Daniele Ilmini from Politecnico di Milano in Italy, and Giacomo Pedretti from the Artificial Intelligence Research Lab at Hewlett-Packard Labs, right here in the United States. They've given us this amazing roadmap to the future of computing.
Yeah, what's truly fascinating here, and what Daniele Elmini and Giacomo Pedretti lay out so clearly, is how RRAM directly tackles this fundamental challenge in modern computing. It's often called the von Neumann bottleneck.
The von Neumann bottleneck. Okay, I've heard that term. What is it exactly?
Well, imagine your computer is like a super efficient office worker.
Yeah.
But they have to run to this giant library that's the memory for every single piece of information.
Okay.
Bring it back to their tiny desk, that's the processor work on it, and then often run it all the way back to the library.
Yeah. Wow, that sounds exhausting.
It is. And this constant back and forth takes a huge amount of time, creates delays, and just sucks up an incredible amount of energy.
Okay, so RRAM fixes this.
RRAM changes that entire workflow. It's like bringing mini desks, or maybe just the ability to process the information right into the library shelves themselves.
So no more commuting for data.
Exactly. No more endless commuting.
That analogy clicks immediately. It sounds like we're literally redesigning the fundamental way computers have worked for, decades?
Pretty much.
But RRAM, it sounds super high-tech, maybe even a bit sci-fi. So at its core, what exactly is it? How does it do this magic?
Well, at its heart, RRAM is actually quite elegant, conceptually. It's a memory device that can physically change its electrical resistance when you apply specific electrical pulses.
Resistance, like how much electricity can flow through.
Precisely. Think of it less like a traditional light switch that's just on or off, maybe more like a tiny, reprogrammable dimmer switch.
Okay, a dimmer. I get that.
And most RRAM devices have this very straightforward structure. Metal, insulator, metal.
Or
MIM for short.
Okay, metal, insulator, metal. I'm picturing a tiny sandwich again. What happens inside that sandwich?
Exactly.
Yeah.
You got two layers of metal, and in between them, a thin insulating material that doesn't normally conduct electricity well.
Right, insulator.
But the key is we can apply a voltage and, in a very controlled way, form this tiny, almost hair-like electrical pathway right through that insulating layer.
A pathway, like a wire.
Sort of, yeah. Researchers call it a conductive filament, or CF. When that filament forms, the resistance drops way down and current can flow easily. That's like your on state, or maybe a low resistance state.
Okay.
Then, when we apply a different voltage, we can break that pathway, rupture that filament, and the resistance goes back up. High resistance state.
So you're literally building and breaking a tiny bridge for electricity inside the material.
That's it, exactly.
That's wild. It's like a microscopic, reversible demolition and construction crew working constantly.
Precisely. And what's really fascinating, while the modern way we do this is cutting edge, the basic idea isn't entirely new.
Oh, really?
Yeah, Daniele Elmini and Giacomo Pedretti's review points this out. Early reports on these resistive switching phenomena actually date back to the 1960s.
The 60s? Wow.
Yep. Pioneering researchers like Hickmott and Simmons and Verteber, they were already studying reversible electrical breakdowns in thin metal oxides, things like silicon oxide or titanium dioxide.
So the seeds were planted way back then.
Absolutely. Imagine Back in 1965, you had scientists like Hyatt and Hickmott publishing in Applied Physics Letters, demonstrating what they called bistable switching.
Bistable, two states.
Exactly. It could reliably be in two stable states, high resistance or low resistance, using materials like niobium oxide. They were basically laying the groundwork for non-volatile memory long before we had the tools to shrink it down and control it like we can today.
So it's non-volatile memory, meaning it remembers its state even when the power's off, right? Like a USB stick or your SSD.
That's the key.
Yeah.
Non-volatile.
But RRAM is potentially much faster, smaller, and maybe able to handle more complex information than those older techs.
Exactly right. And a crucial advancement for modern RRAM is something called bipolar switching.
Bipolar switching. Okay, what's that?
Well, think of it like this. With some older methods, maybe unipolar, you might use the same type of electrical signal, say positive voltage, to both turn the switch on and off, just at different strengths.
Sounds tricky.
It can be. It's a bit like trying to open and close a door by pushing with the same hand, just hoping you push hard enough or gently enough. Bipolar switching is more refined.
How so?
It means we use one polarity of voltage, let's say a positive pulse, to set the device into its low resistance state, like firmly pushing the door open.
Okay, set.
Then we use the opposite polarity, a negative pulse, to reset it back to its high resistance state, like firmly pulling the door closed.
Push and pull.
Opposites. Exactly. This gives us much better control, much better reproducibility, and a clearer difference between the on and off states. And that's absolutely vital for reliability, if you're going to use billions of these things.
Okay, this makes sense. But here's where it gets really interesting and where this deep dive truly goes deep. Researchers aren't just making these tiny switches, they're fine-tuning them at an almost, unimaginable atomic level. For those of us who aren't material scientists, can you boil down why fiddling with atoms is such a big deal here?
That's a great question because, that's really where the rubber meets the road in terms of making RRAM practical, reliable, ready for prime time. A huge amount of effort goes into what we call stack optimization and device engineering.
Stack optimization.
Yeah, remember that metal insulator metal sandwich? The stack is all those layers. Optimization is about creating the perfect microscopic environment for that conductive filament to form and break reliably, millions, maybe billions of times without failing.
Like building a super durable bridge.
Exactly. Think of it like a master chef, precisely layering ingredients to get the perfect flavor and texture. For RRAM, researchers are strategically adding incredibly thin layers, sometimes just a few atoms thick, to precisely control the chemistry inside.
Oh.
For instance, work by teams including Chen, reported in the IE International Electron Devices meeting back in 2009, and later by Young Fisher and colleagues in IE Electron Device Letters in 2013, showed something really clever. By introducing a thin titanium cap layer between certain electrodes and the main switching layer, often hafnium oxide, they create what's called an oxygen exchange layer.
An oxygen exchange layer. Okay, what does that do? Sounds complex.
Well, it sounds complex.
Yeah.
But the idea is pretty neat. It helps control the movement of oxygen atoms within the insulator, specifically creating or managing oxygen vacancies.
Vacancies, like tiny holes where oxygen should be.
Exactly. Tiny missing oxygen atoms in the material's crystal structure. And it turns out these vacancies are absolutely crucial for forming that conductive filament we talked about. So by carefully controlling them, researchers can dramatically improve the device's performance, its stability, its reliability. It's like engineering the material from the inside out to behave exactly how you want it to.
Incredible precision.
It really is. And they're also exploring things like bilayer structures. For example, Kim and colleagues wrote about this in ACS Nano in 2014 using tantalum oxide layers.
Yeah.
The idea is one layer does the actual switching and another layer right next to it acts like a tiny built-in safety resistor.
A safety resistor. To prevent what?
To prevent the device from getting too much current during the switching process, which would damage or destroy it, it adds robustness.
That's smart engineering. And okay, for real, wow. In fact, you mentioned it gets even smaller. Researchers are building RRAM using 2D materials, like literally one atom thick.
Pretty much. Materials that are just a single atomic layer thick, like graphene is the famous one, but here maybe something like molybdenum disulfide, MoS2.
Molybdenum disulfide, okay.
Yeah, Geese and his team, writing in Nanoletters in 2018, they actually coined the term atom resistor for these devices.
Atom resistor, like atom resistor.
Exactly, to highlight this incredible, almost two-dimensional thinness of the switching layer. Imagine a memory device so thin it's practically flat, measured in just the height of atoms.
That's mind-bending.
It really opens up possibilities for incredibly dense memory, packing way more storage into the same space. It's like going from building a skyscraper to designing a sprawling but ultra-thin city on a tiny chip.
Okay, so let's recap quickly. RRAM is tiny, it's non-volatile, remembers without power, and its behavior can be precisely tuned right down to the atomic level. Sounds powerful. But how does all this help our computers think differently? How does it tackle that von Neumann bottleneck we started with?
Right, that brings us to the really exciting part. How can we actually move the computation into the memory itself? This is the core idea behind in-memory computing, or IMC.
In-memory computing, okay.
And RRAM's ability to store information not just as on or off, binary 0 to 1, but as these varying levels of electrical resistance, a whole spectrum of values makes it uniquely suited for performing calculations right where the data lives.
Like those mini calculators built into the library shelves.
Exactly like that. Doing the math right there on the shelf. No need to run the book back to the desk.
Okay, let's talk about AI. Artificial intelligence, especially things like neural networks that power facial recognition or language translation, relies on just massive amounts of repetitive calculations. I think they're called matrix vector multiplications. Can ARM actually handle that kind of heavy lifting?
Absolutely. And honestly, this is one of RRAM's potential killer apps, RRAM crossbar arrays. Just imagine a grid, like a checkerboard, made of these tiny RAM cells at each intersection.
Yeah, like a grid?
These grids are perfectly designed for accelerating exactly those calculations. Each RRAM cell's conductance, remember, how easily electricity flows through it, can be programmed very precisely to represent a weight in the neural network.
Oh, wait, like how important a connection is in an artificial brain.
Exactly like that. It represents the strength of a synaptic connection. Now, when you apply voltages to the rows of this RRAM grid,
Yeah.
just fundamental laws of electricity, Kirchhoff's and Ohm's laws, they naturally do the math. They perform the multiplication of the input voltages by the stored weights, conductances, and sum up the results along the columns.
Wait, the physics does the math automatically?
Yes, it happens physically, in analog, instantaneously, and this is key, all in parallel across the entire array at the same time.
Whoa. So instead of a normal processor doing millions of calculations one after another sequentially,
Right.
the RRAM array does them all at once, just based on how the electricity flows through this grid.
That's the power of it.
That sounds like a massive win for energy use and speed, almost like a giant analog supercomputer on a chip.
Indeed, it's a completely different way of computing. A really prime example of this is the NeuRAM chip. This was unveiled by Juan and a large team in Nature just back in 2022.
NeuRAM.
Yeah, it's a compute memory chip built with RRAM. It includes 48 cores, and each one is capable of multiplying these big 256 by 256 matrices right in memory.
That's huge.
It is. And they demonstrated some really clever techniques like using voltage mode sensing to cut power consumption way down. They also use software tricks like noise-aware training and doing some on-chip fine-tuning to get really impressive accuracy. 85.66% on a standard image test called CIFAR 10. And that's even with the natural variations, the slight imperfections you get in RRAM devices.
So they can work around the imperfections.
Exactly. And a key factor in NeuRAM's success, something Giacomo Pedretti and his colleagues highlighted in the IE International Reliability Physics Symposium in 2021, is RRAM's multi-level programming capability.
Multi-level, meaning more than just on or off.
Right. A single ARM device isn't just binary, 0 or 1. It can be reliably programmed to hold several distinct levels of resistance, maybe 4 levels, 8 levels, 16, representing multiple bits of information in one cell.
Ah, so it's denser. Like going from a simple light switch to a dimmer that has, say, 16 distinct brightness settings.
Precisely. This density is crucial for packing the complex information needed for modern AI into a small space.
Okay, that's running AI models inference, but what about training AI? That's even more demanding, right? It requires constantly updating all those weights as the AI learns. Can RRAM keep up with that incredibly dynamic, continuous learning process?
Training definitely presents its own fascinating set of challenges. It requires a lot of what we call dynamic in-memory computing.
Dynamic IMC.
Right, meaning you're continually making precise adjustments to the RRAM's resistance over and over and over again. And this immediately brings up issues like endurance.
Endurance, like how long it lasts.
Exactly. How many times can you program an RRAM device, set it, and reset it before it starts to wear out or become unreliable?
Is that a big problem?
It can be. As Bellotti and a team showed in IE transactions on Electron devices back in 2015, there's often a tricky trade-off. You might be able to get a really wide range of resistance states, which is good for storing lots of detail.
Right.
but that might actually reduce how many times the device can be reliably reprogrammed before it fails. It's a balancing act.
What else?
Another hurdle is that the way RRAM changes its resistance isn't always perfectly, linear or symmetric.
Hmm.
Agarwal and colleagues discussed this in the International Joint Conference on Neural Networks in 2016. Imagine trying to draw a perfectly straight line up and then back down, but your pen always wobbles a bit or goes up faster than it comes down.
Okay, so the changes aren't perfectly predictable.
Not always perfectly. And for training AI, where you need these tiny cumulative updates to be accurate, that nonlinearity or asymmetry can cause problems, make the learning less stable.
So this continuous AI learning needs super reliable, consistent changes to those RRAM weights. What are researchers doing to make sure these tiny switches can learn effectively without, wobbling or wearing out too fast?
Well, they're tackling it from both software and hardware angles.
Yeah.
On the software side, researchers are developing really sophisticated algorithms. One clever approach is called the tiki-taka algorithm.
Tiki-taka, like the soccer strategy.
Exactly like that, borrowing the name.
Yeah.
Proposed by Gockeman and Heinz in Frontiers in Neuroscience in 2020. The idea is it's like a smart coaching strategy for the RRAM device updates. It helps mitigate those errors caused by non-ideal behavior, making the overall learning process more robust and accurate.
Clever. And on the hardware side?
On the hardware side, people are engineering new RRAM devices specifically designed for training. For example, Stacconi and his team, writing just recently in Nanoletters in 2024, developed a new type of RAM stack. Remember those precisely engineered layers?
Yeah.
This new stack enables much more symmetric potentiation and depression.
Okay, potentiation and depression. Are we still talking memory chips, or is this a therapy session?
Good question. Yeah, in neuroscience and neuromorphic computing, potentiation basically means strengthening the connection in RRAM terms. That's lowering the resistance. And depression means weakening the connection, increasing the resistance.
Got it. Stronger, weaker.
Right. And Stacconi's team created a device where those strengthening and weakening steps are much more symmetrical, much more equal and opposite. And that's exactly what you need for these AI training algorithms to work accurately without significant drops in performance due to the device's imperfections.
Okay, so RRAM superpowers aren't just for neural networks and futuristic AI then. Can it help us with other kinds of complex computing tasks too?
Oh, absolutely. Not at all limited to the deep learning. RRAM can accelerate a whole wide range of machine learning and just general mathematical tasks that are bottlenecks today. Well, think about common problems like linear regression or principal component analysis, PCA. These are critical tools in everything from financial modeling to, analyzing scientific data. And mathematically, they involve solving complex matrix equations.
Okay, more matrix math.
Yep. And Sun and his colleagues published some really groundbreaking work on this in Proceedings of the National Academy of Sciences, PNAS, in 2019, and also Science Advances in 2020. They demonstrated how RRAM crossbar arrays, when you combine them with some clever analog feedback circuits, can actually solve entire systems of linear equations and perform regression analysis in basically a single computational step.
A single step for the whole problem.
Essentially, yes. The physics of the circuit finds the solution almost instantly. It's like having a calculator that, instead of crunching numbers line by line, just looks at the whole page of complex equations and instantly gives you the final answer.
Wow, that must be way faster.
Orders of magnitude faster than doing it digitally on a traditional processor. And then there's another area, tree-based machine learning.
Decision trees, like for recommendations or diagnoses.
Exactly those. Pedretti and his team showed in Nature Communications in 2021 that you can build something called analog content addressable memories, or CAMs, using memristors, which RRAM is a type of.
Analog CAMs. Okay.
These CAMs can massively parallelize the process of searching through those decision trees during inference. Basically, they can check many paths or conditions simultaneously, leading to huge speedups for those kinds of algorithms, too.
This all sounds, well, it sounds like we're getting closer to making computers that don't just process information faster, but maybe actually think a bit more like biological brains?
That's precisely the ultimate goal, or at least one of the major ambitions, of the whole field of neuromorphic computing.
Neuromorphic. Brain-like.
Right, to emulate the brain's incredible efficiency and its processes like learning, adaptation, memory, directly in electronic circuits. I mean, the brain is the ultimate example of in-memory computing, right? It processes and stores information in the same place. The synapses act as both memory elements and computational units. And as Elmini Wang and Liu highlighted in a review in APL Materials in 2021, RRAM devices offer some really unique properties that seem perfectly suited to mimic these crucial neurobiological processes.
Like what specifically? How exactly can a tiny RRAM switch mimic the incredibly complex workings of, say, a neuron or a synapse in the human brain?
Well, a key thing RRAM can emulate is synaptic plasticity.
Plasticity, the ability to change.
Exactly. It's the brain's fundamental mechanism for learning and memory. It's how the connections, the synapses between neurons, get stronger or weaker over time based on how active they are.
Okay, and RM can do that.
Yes, we talked about potentiation, strengthening and depression, weakening. RRAM can do both. There are different types of plasticity too. Long-term potentiation, LTP for lasting memories, and short-term potentiation, STP for more temporary ones.
Right.
And one of the most famous learning rules in neuroscience is spike timing dependent plasticity, or STDP.
STDP, what's that?
It's a rule where the precise timing of electrical signals, or spikes, arriving at a synapse from two connected neurons determines whether that connection gets stronger or weaker. It's thought to be fundamental to how we learn associations.
Timing is everything.
Exactly. And Pedretti and his team, back in Scientific Reports in 2017, beautifully demonstrated STDP using RRAM devices acting as artificial synapses. They showed how this could enable unsupervised learning, where the system learns patterns without explicit labels by selectively strengthening connections for patterns that occurred repeatedly with the right timing. It's like the RRAM synapses were learning to recognize what's important all on their own.
That's amazing, learning from timing. What else?
Now, for something a bit different but equally brain-like, short-term memory. You might think all memory devices should hold information forever, non-volatile, right?
Yeah, usually.
But for mimicking certain brain functions, sometimes you actually need volatile RRAM devices, devices that intentionally forget.
Okay, hold on. A memory that intentionally forgets, why would you possibly want that in a computer?
Because our own brains do it all the time.
Yeah.
It's like your temporary working memory. You hold on to a phone number just long enough to dial it, then poof, it's gone. These volatile RRAM devices, like some demonstrated by Wang and colleagues in Advanced Intelligent Systems in 2021 using tiny silver nanodots,
Okay.
they only maintain their on state, their low resistance, for a brief, predictable period before they naturally decay back to the off state.
And that's useful how?
It's crucial for processing information that changes over time. It allows for things like spatiotemporal pattern recognition, recognizing patterns that unfold in both space and time, like understanding speech or interpreting gestures in a video. The memory needs to fade to be ready for the next piece of the sequence.
Ah, okay, so the forgetting is part of the processing.
Exactly, and what's even more mind-blowing, perhaps, is using this for things like tonotopic frequency detection.
What?
Tonotopic. Think sound frequencies like musical pitch. It's about processing auditory signals in a way that's inspired by how the human cochlea, our inner ear, works.
Seriously, mimicking the ear.
Yeah. Wang and his team, in work published in Nature Communications in 2019 and also presented at an IE conference in 2024, showed how arrays of these volatile RRAM devices can mimic this. The number of devices that get activated actually increases with the logarithm of the sound frequency. It responds to different pitches in a way that mirrors our biological hearing.
That is truly remarkable.
Yeah.
Using the temporary fading nature of these devices to process information in real time, just like our brains handle a fleeting sound or a quick visual cue. It's almost like giving computers a form of sensory intuition.
That's a great way to put it. And reservoir computing takes this concept even further.
Reservoir computing.
It uses a dynamic layer, a reservoir, of RAM devices, often volatile ones, but crucially with tunable retention times.
Tunable. You can control how long they remember.
Yes. You can engineer them or electrically tune them to hold their state anywhere from milliseconds up to seconds, as Wang and others showed in Nature Communications 2019 and IE 2021. This flexibility allows the system to process really complex time-dependent signals like continuous speech or maybe video frames converted into sequences. It provides this inherent real-time adaptability, which is seen as an essential building block for creating truly sophisticated, brain-like neuromorphic systems.
Okay, wow. This has been a journey, so let's try to pull it all together. What does this all mean for us, for the listeners, and for the future of technology? I mean, from drastically speeding up AI, both running it and training it,
Yep, inference and training.
to solving complex math problems that are bottlenecks now, and even building chips that actually mimic the amazing learning and memory tricks of the human brain?
RRAM seems like a really powerful, really versatile contender for the future of computing.
It really does. It gives us non-volatile storage, incredibly low power use, amazing potential for shrinking things down, and this ability to store multiple levels of information. It just feels like a true game changer.
It certainly has that potential. But, this also raises an important question as we look ahead. While RRAM offers this immense promise and incredible versatility, there's still careful engineering needed, right, to bring it to its absolute full potential.
Right, it's not magic yet.
Not quite magic yet. As we've seen today, different applications really demand different RRAM properties. Some applications, like AI training, need incredible endurance, billions of cycles. Others, maybe for scientific computing, need ultra-high precision in those resistance levels.
Okay.
Some need really long data retention, like for archiving. While others, like those neuromorphic systems, actually thrive on volatile short-term memory characteristics. And then there's always the challenge of getting those electrical characteristics, the switching, to be perfectly linear and symmetric when you need them to be.
So different jobs need different tools from the RRAM toolbox.
Exactly. The ongoing challenge, but also the excitement, lies in finding that perfect balance, in continuously optimizing the RRAM devices themselves and the circuits around them for all these diverse and demanding requirements.
Yeah.
It's definitely not a one-size-fits-all solution. It's more like a whole new toolkit with incredible possibilities.
And maybe that's the big picture takeaway I hope everyone listening remembers. The future of computing isn't just about making traditional processors faster or just cramming more transistors onto a chip following Moore's law. It seems like it's about fundamentally rethinking the entire relationship between memory and processing.
A paradigm shift.
Exactly. And RRAM looks like a key player in that revolutionary shift. It's moving us closer to devices that aren't only vastly more energy efficient and powerful, but also potentially far more intelligent in how they handle and learn from information, finally breaking free from that old von Neumann bottleneck.
That's the hope.
So here's a final thought to chew on. As we continue to push the boundaries of RRAM and this whole idea of in-memory computing, how might these innovations not only power the next generation of AI, making it faster and more efficient, but maybe, just maybe, also deepen our own understanding of what intelligence itself truly is?
That's a deep one.
Something to think about next time you're waiting for your app to load. Or maybe, just maybe, with ARM powering things in the future, you won't be waiting at all.